Hello and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mounts, and I'm glad that you've taken the time to join us today as we look at our topic of how to calibrate your torque analyzers and sensors. So if this is a topic that you want to learn about, or if it's something that you're looking to bring in-house for calibrating your sensors, this is going to be the discussion for you. So with that, let's go ahead and jump right into today's presentation. So what is calibration? Calibration is basically measuring or validating a measurement device to a higher standard than the actual device itself. And so as it relates to torque sensors, we do a calibration on those sensors to make sure that those sensors are accurate and performing correctly, because those items are then used to calibrate tools, hand tools, power tools, and things like that that could be used in very critical type applications. And if those applications fail, then there can be real issues. So this is the reason why we calibrate our torque analyzers and sensors along with other items within the manufacturing process. So there are a number of different calibration quality standards that can be applied to a particular type of standard as it relates to calibration. So ISO 9001 is a standard. It's not necessarily related to calibration itself, because the ISO 17025 falls underneath the ISO 9001 certification, but both of those work kind of hand in hand. One is the recording of information, and then the ISO 17025 or 025 is the actual laboratory calibration accreditation for those particular types of testing. There's also the ANSI Z540, which is another standard. And then there are some other ones that are available as well. The NVLAP, which is the National Volunteer Laboratory Accreditation Program, which falls under labs and companies that do work in conjunction with the government. And then we also have a British standard and also a German standard as well. And those standards will determine how you do whatever calibration that you are going to be using. And so what calibration options do you currently have at your disposal? So there are about three that you can use. One is going to be you take your sensors and analyzers, and those get sent out to an outside calibration lab, or they can be sent back to Mounts if you're using a Mounts product. Currently, Mounts has three labs. We have one in San Jose, California, one in Foley, Alabama, and then we also have one in the UK. So you can send those out to us or to any other calibration facility, and those analyzers and sensors can be calibrated. You can also have a mobile calibration company come into your facility and do the calibration on site. Or lastly, you can have the calibration done internally, in-house, for whatever type of sensors that you have. That does require a bit of an investment for that, but it depends on how many sensors you have, and again, the personnel to go ahead and implement that if you do want to bring that in-house. But those are typically the three options, or it could be a combination of any of those in conjunction with the calibration cycle. So that's going to bring us to our poll question for today. So our poll question is going to be how do you do your calibration with your torque sensors? Do you use an outside vendor or do you do them internally? So we'll go ahead and give you a second or two to run that poll, and we'll continue here in a second. All right. Thank you very much for participating in that. It looks like about 75% or so use outside vendor services for their calibration, and about 25% or so do it in-house. So what is involved in the calibration process, and one of those items is going to be the calibration interval. And so at what point do you go ahead and recalibrate a torque sensor within that that setting? So mounts, we typically will recommend a 6-month calibration window for sensors that are newly purchased, but it's really going to depend on your internal process and what you think is going to be best for your particular process or your level of heightened accuracy for a certain sensor, depending on the application, for the tools that may be used on that application. And that interval can change basically dependent on the particular application or the sensor that's being used. And so we typically recommend 6 months. Often we'll do a 12-month calibration. After a certain period of 6-month calibrations, if you would like to do that. Some companies will request a 12-month. They may request an 18-month calibration cycle. So it's really dependent on, again, your level of need for the type of applications that you may have. A 12-month may be sufficient, or even extending that out to 18-month, depending on the certain parameters around how that sensor may be functioning within the calibration process. Now, how does a torque sensor actually work? So we are taking an analog signal that is being generated by a tool, and then we are converting that to a digital signal that is giving us a readout of what the torque was that tool applied. And so how does this actually function? And it's all done through the use of resistance measurement. So there is a device, you may be familiar with it, maybe not, but a strain gauge is an electrified circuit. It's very small, less than a postage stamp size of a circuit. And this particular circuit is then laminated onto a piece of stock. And as we apply torque to that stock, there is torsion that happens, and it changes the resistance that we see within the strain gauge because it's actually changing its geometry as that stock is being applied with torque. And so we basically are developing a correlation between the amount of deflection that may be happening in the strain gauge to the amount of torque that is being applied. And this animation can kind of help explain that. So we have our strain gauge laminated to our stock, and as the torsion happens on the stock, we do get some deflection in the actual strain gauge, again changing the resistance value that we are getting through that electrified circuit. And here's an example of one that is off of a screwdriver type of sensor. Again, we have the strain gauge on the stock, and then as that flexes or the torsion happens, we're able to measure the resistance through that circuit. So the calibration equipment that you would need if you want to do this type of testing in-house are going to be segment arms, wheels, weights, hangers. This is the type of equipment that you would need, as well as a way to position or a bracket to hold the sensor or analyzer that you may be testing in, that we would be able to actually implement the use of the hangers and weights. And so in our typical torque formula, we have distance times force is going to equal what our torque value is. Now, there's a couple other calculations that go into it, like a specific gravity of where you're at, and that can change depending on your location, and that is a variable that is included within the actual process of doing the measurement for the different values that are being taken. But a typical 3-point calibration is going to test or apply load to the sensor at 10%, 50%, and 100%. And so by using the wheels and the weights, or the segment arms and the weights, we develop a value for that. So as we look at our demo for today, we have a 2-foot segment arm that is going to be measuring a 200 foot-pound sensor. And to do that, to get to 10%, 50%, and 100%, we'll basically use half of the weight that you would, because of the length of arm. So at 10%, we would be using a 5-pound weight, which is going to give us 10-pound weight, which is going to give us our 20% value, and so on as we move through the actual percentage. But these are the calibrated weights that are used as part of the traceability that go into the actual list of the traceability if you were to run that from a specific tool. That tool then is traceable to the analyzer, and that analyzer eventually is traceable to the actual weights, which are, again, accurate and calibrated to their specific weight. So let's go ahead and look at the demo that we have. And this, again, is an LTT 200 F, or 200 foot-pound sensor. And we'll use the 2-foot segment arm. And this is an image of the software program that we will go ahead and use to capture the information and to program the actual information onto the ARC2 chip, which is located inside the sensor. And the first thing that is done is we actually need to exercise the sensor. So we put a 100% value or 100% weight onto the sensor, and then we let it hang there for about 30 seconds to a minute or so, just to exercise that particular sensor. So I have cut out the actual waiting part, so we're not sitting here waiting for that to happen during the actual calibration process. And so as we begin the actual calibration process, again, we're going to start at 10%. So we will use the hanger and a 5-pound weight to get us to our 10-pound value. And as you can see, the actual process of making sure that the weights are put on very gently and that they remain still, so we don't get any variation in the torsion that may be happening during the process. And then that value is stored in the system. And then we'll move on to the 50% value. And the system is allowed to go ahead and calculate, again, the resistance that it is seeing out of the string gauge, and then putting that calculation onto the chip that, again, is stored inside the sensor. And so if we were calibrating a standard sensor that isn't necessarily in the actual analyzer, like it is here with the LTT, we would be able to plug that sensor into either another LTT or a PTT analyzer, and all of the calibration data that is being done here is stored on that chip, and it is sent to the analyzer for it to be used. And now we simply do the 100% value. And currently this is all done in the clockwise direction. And then after this particular part is finished, we'll go ahead and we flip that segment arm around and do the exact same readings for the counterclockwise direction. And then the system will go ahead and calculate the all of the data information for that, and then that is sent to again the ARC2 chip, where it will remain. Now, systems are generally calibrated in one direction, but we do verify and make sure that it is done in the reverse or in the counterclockwise as well. And then the system does get another check to make sure that everything is correct within that calibration process. So all in all, it's not a terribly complicated type of execution, but it does require, again, the investment in the personnel, in the weights, and the wheels, and those do need to be maintained in a calibrated state as well. So with that, I hope that gave you some insight in how sensors are calibrated. And with that, we're going to go ahead and move to our questions and answer section. So, Chris, do we have any questions?
Hello, Dave. One question we have is, do you have to apply a positive bias before zeroing in the direction of the calibration?
So typically, when we're doing that, we'll exercise the joint to 100%. The actual calibration will um, be at starting at 0. If there is any type of offset that we see in there, that will be accounted for if it is very low as far as the AD counts are concerned. But if there is too much deflection in that, then there may be an issue with the actual gauge itself. It may have been over torqued. So the calibration process does allow for a slight variation at 0. Then it will go ahead and make that calculation at the 0 AD point. But if it is greater than a certain value of AD count, then the sensor may be damaged. So,
All right, Dave. Another question we had is, they wanted clarification on, you said calibration is only done in one direction. Is that what you were saying at the end?
uh, I'm sorry. It is done in both directions. I believe it's maybe just the tools that we do that are one direction only. The calibration process does account for both directions.
Okay. Another question we had was, how often do we see instances where adjustment is required versus verification?
It's really going to be very dependent on the use of the analyzer. So it's kind of a difficult question to give an exact answer. You may be in an area where you may have people that kind of understand what's happening with that, and the use of that particular sensor. Again, if there is any type of over torque that may happen to a particular um, sensor, that is going to possibly introduce an offset for the actual strain gauge. Because if we take the torsion that's happening on that stock too far, that strain gauge in there as it flexes and changes, if it goes to a point um, that it cannot return to its original shape, then we're going to see an offset from the 0 point, and that gauge may be damaged, and that would need to be replaced. So it depends on use and who may be doing the actual using of the sensor.
All right. Another question we had was on mounting positions during the calibration, where their static sensors might be particularly sensitive in a certain orientation during the calibration process.
Yeah, so all of the dead weight type of hanging is done in a vertical type of calibration. So brackets are typically designed and made for specific analyzers or specific sensors, and so those all are done in the weights going vertically. So that can be changed, obviously, through the use of different segment arms and different weight values that are going to give us our distance times force. So those types of things can change, but all of the dead weights happen in the vertical orientation.
All right. Another question we had was: Is there software that's required during the calibration process?
For the mounts products, yes, it would be um, the software that we provide with the uh, either the PTT or the LTT software. And within that, there is the calibration software that is part of that package. It is password protected, but if you do want to use that, that is available to be used. But yes, you do need the software package to be able to write the values to the ARC chip, ARC2 chip within the sensor.
All right, Dave. Another question we had is: If the torque analyzer meets the specification, but is at the extreme upper and lower tolerance, at what point do you make the decision to make an adjustment?
Um, it's within tolerance. It's going to depend on the actual, I guess the how far it may be close to the specification um, within that range. And so that is going to be determined um, within what that value is. And so if we're really close to that range, there may need to be some adjustment made to get it more in line with the specification, even though it might be on, or if it is close to the extreme uh, level of accepted.
All right. Another question we had was: How do you use zero reference transducer?
So they're with the mounts product, either the LTT or the PTT with those sensors, they will. There is no zeroing to them. Um, when you reset the sensor after a reading, it should go to zero. Um, During the calibration process is when that zeroing happens. So there's not a zero function that is on the analyzer itself. Again, if we clear a reading and the system does not return to zero, then we know that there may be an issue with the sensor that is showing either a negative or a positive offset. And the link and gauge may be damaged, which is typically by an over torque event that happens on that particular sensor.
All right. On the calibration frequency, you mentioned it's based on time, or is it, or can it also be calculated based off like a number of torque cycles that it's used on?
So typically, when we're dealing with sensors, you'd want that to be on a time interval base. If you are looking at validating or calibrating tools on that sensor, that could be something that can be definitely done by a use type of interval and performance based type of calibration. But the sensors themselves should be on a schedule.
All right, Dave, that's all we had for today.
All right. Thank you so much for joining us today. Really appreciate that. Look forward to having you next month in our topic. So have a great day and take care.